require some heat flow from the system into or out of the system, right? Whether you're melting, freezing, vaporizing, something like that. So you can get the phase change. You don't know what the entropy of the system is necessarily, but you can get the heat flow of the system by delta H vaporization, delta H fusion, all that stuff, right? How much heat do I need for this phase change? Then you can calculate that delta S of the surroundings right away when you know the temperature. And then once you know this, you know for a phase change that the delta S of the system is the negative delta S of the surroundings from this equation right here, because the delta S of the universe is 0. So in a phase change, you don't figure out the entropy of the system first. You figure out the entropy of the surroundings based on the heat flow. You need the Q of the system, so you need to know how many moles or how many grams are vaporizing, you know, just like we did in class today. So you need to figure out how much heat that phase change is going to take. But then you can calculate the delta S of the surroundings, and then you can relate that right to the delta S of the system. But that only works for this special case of a phase change. If you don't have a phase change, you have to go to this delta S of the reaction, or you have to go to the free energy. You know the delta S of the universe is going to be greater than 0, and so you have to work your way through it like that. Yeah?
So we had one on the homework where you had to compare like entropy in H2 and then SO2. Like what are the rules when you're comparing two compounds like that?
Yep. So more atoms is higher entropy. Higher temperature is higher entropy. Lower pressure, higher entropy. So more atoms is more entropy. Or more moles. Okay? Yeah?
What if it was like, I don't know, if like two different compounds with their two different charges. So like they're the same compound with two different charges.
Same compound, two different charges. So like sodium 0 versus sodium plus.
Yeah.
Well, I mean, you can't have solid sodium plus, right? So I suppose you could have sodium 0 in the gas phase and sodium plus in the gas phase. Which one has more particles in it? If you count up all the electrons, protons, neutrons, all of that stuff.
The one that's 0.
Sodium 0. So that might have a little bit more entropy, right? Because it's got that extra electron, an extra degree of freedom. But that's a very special case. I won't give you anything that difficult. More questions on entropy? Okay, so you have two blocks. So you have a 100-gram piece of iron at 300 degrees Celsius. And you have a 25-gram piece of iron at 50 degrees C, and you push these together. What's the final temperature? This is the problem that you're asking about, right? Okay. So when I push these together, what's the heat flow going to look like? Where's the heat going from where to where? Going from this thing to this thing. So Q is going to go that way. Q going out of something is positive or negative? There's negative Q here. Q going into something is? Are these numbers equal? Yeah, they're going to be equal, right? So all we need to do is we need to figure out the Q. So how do we figure out a Q when there's a temperature change? What do we need to know? Q is M times C times delta T. Mass, heat capacity, change in temperature. What are the units of heat capacity? Joules, mole, or joules per gram, Kelvin. This is often called the specific heat capacity because it's mass-based. This is called the molar heat capacity. And so all we need to do is we need to set this Q equal to negative that Q. So we just take mCp delta T equals negative mCp delta T. We just plug everything in and we solve. So, mCp. So since these things are both made out of iron, right, we can cancel the CP's from both sides because that's the same number. They both have the same heat capacity, right?
Wait, they're both iron?
Oh, sorry, Fe. It's not made out of fluorine. There we go. Fe. They're both made out of iron. Now, if one was water and one was aluminum, we have to put the heat capacities back in there, right? Because water will carry more heat with it than aluminum for a given temperature change. Okay, so what do we put here for mass? Why do you want to put the combined mass in there? Heat's going from, remember we just set this up, right? Heat's going from this into there, right? So what do we want to put? 100. 100 grams. What's the delta T of this one? 300 minus what? T final. Right? So this block is going to cool down from 300 to something. And so the amount of heat that that's going to take is 100 times 300 minus something. So this gives us the quantity of heat that's going to come out of this block. And the heat's going to go into this block right here, right? Because all these things are going to do is exchange heat. Yeah?
Does the temperature have to be in Kelvin?
It can, well, yeah, we'll put it in K in a
Right.
second. It doesn't matter for these delta T, unless you go negative, right? Because if you have a negative temperature, you're going to get goofed up if you use Celsius. So let's do, what's 300 plus 273? 573. Great. Let's keep it all in K so we don't goof ourselves up. Okay, so the heat's going to flow out of this one. It's going to flow into this one. So we have 20 here, right? Or 25, sorry. 25, no CP. What's the delta T of this block? What's going to happen? Temperature's going to go up, right? And so to get a negative number here, 25 grams is always positive, right? This delta T is going to have to be negative. So this is T initial. So it's 50 plus 273 is 323 minus T final. So T final is going to be higher than 323, so that gives a negative number. That's good. Negative times the negative is going to be a positive. This number is going to be positive, right? Because this T final is going to be less than 573. So you can still solve this equation. If you flip this sign around, you can still solve it, but you're going to get the wrong answer because it matters what order you put these in. So you need to check very carefully the sign of the Q, and you need to make sure that this Q is this thing right here. Oh wait, did I totally set it up wrong? Did I? Okay. Yeah, let me fix this. So
So is it the other way around?
there's the negative right there, right? Sorry. T final minus, what do we have? 323, right? So this is going to be a positive number, positive Q. Sorry about that. This is going to be a negative number because this is less than 573, so this is a positive number, negative Q. So now we've got it. So I would have gotten the wrong answer, right? If I didn't check it. Okay, apologies. So negative Q going out, positive Q coming in. We have one temperature, one unknown, one equation, and we can solve it. So the key is to set the Q's equal to one another and watch the heat move from one to the other. Yes? Did I goof again?
No.
Oh, go ahead.
So you have the negative 100 on the left, so it matters which side the negative's on, depending on which one like goes to a higher or lower temperature.
Oh yeah, it matters because the sign of Q matters. Remember, we have our system, right? And so whether Q is going out or Q is coming in, that sign really matters so we can get the entropy calculation correct, we can get the delta T correct.
So on the left, because the Q is leaving the larger block.
The heat is leaving the larger block and going into the smaller block. So this was a homework question, right? Who got the homework question correct? Who understood it? Okay. I also gave you some examples, so there's another example where you take, is everyone good on this block example? Let's see if I can get this one right, just from the get-go here. So say I take 500 grams of water at 298 K, and I drop in 5 grams of aluminum at, let's say, 90 degrees Celsius. What's going to happen? Where's the heat transfer going? From the aluminum into the water, right? So this is negative Q. This is going to be positive Q. So I just have mCp delta T for water is mCp delta T for the aluminum. Which one gets the negative sign? Aluminum. And so I can proceed exactly the same as I proceeded before. I have to put in the specific heat capacity for each of them. I figure out a delta T. So what's the approximate delta T? If you had to guess, what would you guess for the delta T for this one? Or what would you guess for the final temperature? What does your spidey sense tell you? What's that?
308 Kelvin.
308. Good. Why did you guess that number?
Because it's